Hello students, welcome to this video module on electromagnetic wave reflection and transmission at normal incidence. In the previous video module, we discussed about propagation of electromagnetic wave in a linear homogeneous medium. So we discussed about its speed, its relation to the dielectric constant. Then we discussed about energy density and Poynting vector. Now, now we are going to discuss about how this electromagnetic wave behave when it reaches a boundary between two linear media. So we know when any wave reaches a boundary between two media, a part of that reflect back, another part transmits. So in the case of electromagnetic wave also, the same process will happen when it reaches the boundary between two linear media. A part of that wave reflect back and another part transmits. So we have to find an expression for the intensity of transmitted wave and reflected wave. So as a first case, we are discussing about reflection and transmission at a boundary between two linear media and the wave incident at an angle 0 with the normal, or we call it as the normal incidence. Normal incidence means the electromagnetic wave incident normally along the normal with an angle of incidence 0 degree. Be very careful. The angle of incidence is not 90 degree. It is 0 degree because the angle of incidence and angle of reflection is measured with respect to the normal. Normal is always perpendicular to the surface. So along the normal means the angle of incidence is 0 degree. So we are discussing about normal incidence of electromagnetic wave on a boundary between two linear media. Okay, now what are the difference between these two linear media? Their propagation constants k's are different. For the first medium, it signifies the propagation vector is represented by k1, and for the second medium, it is represented by k2. But the the wave, the angular frequency omega, or the frequency of the electromagnetic wave, will not change from one medium to another. If it is omega, it will be omega in the other medium also. We know that frequency is the property of an electromagnetic wave that does not change when it travels from one medium to another. But the propagation constant changes because the speed changes in two media. Speed depends on the dielectric constant of the medium that we derived in the previous module. Speed v depends on the dielectric speed depends on the refractive index, which in turn depends on what is called the dielectric constant of the medium. Okay, now let us go to the discussion about reflection and transmission at a boundary between two linear media and the waves incident normally along the normal. Okay, so here you can see the electric complex amplitude of electric field and the magnetic field is represented. You can see EI complex of Z comma T that represents an electric field vector, electromagnetic wave propagating along the Z axis, along the Z axis. EI is equal to E0I complex e to the power I K1 Z minus omega T X cap. X cap shows the electric field is vibrating along the x-axis because the propagation is along z-axis. So they are perpendicular. Now the magnetic field component. We know the magnetic field component BI complex, comma ZT is equal to B0I complex e to the power I KI Z minus omega T Y cap. Why we took y cap? Any direction perpendicular to both electric field and magnetic field. So in general, we take if x-axis is the electric field component and z-axis is the propagation direction, then y-axis is naturally the selection for magnetic field. Okay, and here you can see that instead of B0, what they mentioned here is E0 by V, because we know that magnetic field B equal to 1 by velocity times electric field. That's a relation between these two. Okay, so the magnetic field amplitude is related to the electric field amplitude with a speed 1 by V times E. And I mentioned in the beginning itself a part of that reflect. So the reflected part of electric field and magnetic field is represented here. ER complex equal to the reflected one, the reflection happens in the same medium itself. Therefore, we are using the same propagation vector K1 there. So ER complex equal to E0 R complex e to the exponential I minus k1 z minus omega t. Here you can see it was plus k1. Here it is minus k1 because after reflection it travels just opposite to the incident one. That is why this minus k1 minus omega t, and that itself in the x cap direction, the same. Then the magnetic field component, it is negative B0 R complex. But they used 1 by V1 times E0R complex because we already mentioned the relation between these two. E to the power I minus K1 Z minus omega t Y cap. And the transmission, and here you can see the speed V1 in the first medium incident and speed V1 in the reflected case also, because the incident wave and the reflected wave are in the same medium. But transmission, that is in the second medium, so the speed will be different. So Et complex equal to E0 T complex e to the power I K2 Z minus omega t. Here it is K2 Z minus omega t, because that's second medium. And magnetic field Bt is equal to 1 by V2 times E0t. This is instead of, what is that? Actually, it was B0t. So instead of B0t, we can use E0t complex by V2 e to the power exponential I K2 Z minus omega t Y cap. So in this slide, you can see the incident wave, reflected wave, and transmitted wave. And you can see the representation also. The vector representation of these fields and the reflection and interface, everything is shown here in this diagram. Okay. Now, the boundary conditions that we already discussed in the previous video module. The boundary conditions require that the first and second, there is no components perpendicular to the surface. So we can just the 1 and 2 are trivial because there is no perpendicular components. Okay, because the propagation itself is perpendicular to that, so there won't be any perpendicular components. Now the third one requires that electric field components on the left must be equal to the electric field components on the right. So E0 I parallel plus E0 R parallel is equal to E0 T parallel. E0 I and E0 R are on the left side and E0 T on the right side. So this is from the third boundary condition. And the fourth boundary condition, requires that 1 by mu1 times, which are the parallel components of magnetic field. There is Bi component and a Br component. So that is what this one. This is Bi minus Br. Because if one is like this, the other is like this. So that is why the minus sign there. Okay, 1 by mu1 times Bi. So instead of Bi, we can use 1 by V1 times E0I minus Br. Instead of Br, we can use 1 by V1 times E0R. So that then 1 by mu1 times 1 by V1 E0I complex minus 1 by V1 E0R complex equal to, on right side it is 1 by mu2 times 1 by mu2 times Bt. But Bt can be replaced by 1 by V2 times E0t. So these are from the third and fourth boundary conditions. Now, slight rearranging this, you can take this mu1. You can take this mu1 from left side to right side. And also there is a V1 common factor. Okay. So you can write this as E0I complex minus E0 R complex equal to V1, mu1 by mu2 times V1 by V2 times E0 T complex. Okay, so just rearranging this equation. And this mu1 V1 by mu2 V2 is given as a term beta. Okay, mu1 V2, mu1 V1 by mu2 V2 is termed as beta. And also we can replace this by again V1. What is V1 actually? V1 is equal to C by N1. V2 is C by N2. The speed of the medium, speed of wave in vacuum and in and N1 and N2 are the refractive index in respective medium. So when you substitute for V1 and V2, you get it as N2 by N1. So beta is equal to mu1 V1 by mu2 V2, or it is also equal to mu1 N2 divided by mu2 N1. Okay. So we simplified the expression for electric continuity of electric field to this boxed expression. Okay. Now, now our aim is to find E0R and E0T in terms of E0I. So we have two expressions here. Which are the two expressions? One is E0. So I can write the expressions here. E0I plus E0R complex equal to E0 T complex. Also, other expression is E0 I complex plus E0 R complex. Sorry, there is a minus sign, right? Minus equal to beta times E0 T complex. So we got two equations. Two linear equations are here in two variables. So we can solve for E0R and E0T in terms of E0I. So how to solve this? First of all, you can solve by I think you can add these two expressions. When you add these two expressions, you will get 2E0I equal to E0T times 1 plus beta, right? So what is E0T from this expression? So E0T complex equal to 2 divided by 1 plus beta times E0I times E0I. That is what this expression. Just a simplification of this, what is called simplification of this equation, these two equations in two variable. And further, now you have to find E0R. For that, similarly, you can subtract the second equation from first equation, and so thereby you can eliminate E0T. So you will get E0R, and E0R is okay. I will show the calculation for E0R also. Okay, we can do that by substituting. So we know the equation E0I plus E0R equal to E0T complex. We now calculated E0T, so we can substitute for E0T. So this become E0I plus E0R complex equal to, instead of E0T, you can substitute 2 divided by 1 plus beta times E0I. Now what we can do is you take the E0I to the other side. We will get E0R complex equal to it become E0 2 by 1 plus beta minus 1, because we are taking one E0I to the other side. So E0I. Then this can be 2 minus 1 minus beta. So 1 minus beta. So 1 minus beta divided by 1 plus beta times E0I. That is the first expression there. Okay. So hence we got the expression for E0R and E0T in terms of E0I, which is the only known thing. We know E0I, that means incident parameters. So using that, we have to calculate the reflected parameter and transmitted parameter. And there's a term beta. Beta is actually what? Beta is the permeability of the medium and the speed or the refractive index of the medium. These are also known parameters. So if you know these two parameters, that means the speed, I mean refractive index and the permeability and the incident parameters, you can calculate the reflected parameter, reflected intensity and the transmitted intensity. That was our aim actually. Now, this is for electric field. In the same way, you have to write the expression for magnetic field also. If you want, you can write, because we know the relation between electric field and the magnetic field. So we got this expression. Now, see, there is another conversion, because this is in terms of beta. So we know beta is actually mu1 v1 and mu divided by mu2 v2. So replace it. So for replacing that, you can substitute for beta mu1 v1 by mu2 v2 divided by mu1 1 plus mu1 v1 by mu2 plus v2. So that arrangement. So let us see how that calculation goes. See, E0 R complex equal to 1 minus, what is beta? It is mu1 v1 divided by 1 divided by mu2 v2. 1 minus, sorry, 1 plus mu1 v1 by mu2 v2 E0 I. Okay. Now taking the LCM for this, you will get mu2 v2 minus mu1 v1 divided by mu2 v2 plus mu1 v1. The denominator mu2 v2 will get cancelled from numerator top and bottom. So it will get like this. Now, there are we know that mu1 and mu2 are approximately same. We know that the permeability of medium, they are very close to the permeability in vacuum. So mu1 and mu2 close to mu0. So we can eliminate that value, and what will get remaining is this is an approximate value, v2 minus v1 divided by v2 plus v1. If you need an exact value, you can substitute that mu1 and mu2 also, but this is also almost correct, almost right. So that is why this expression E0R complex equal to V2 minus V1 by V2 plus V1 E0I. And this is E0T complex in the same way. Now, from the complex notation to the ordinary notation, E0R equal to modulus of V2 minus V1 by V2 plus V1 E0T, and E0T is equal to this one. So E0I. Now, in terms of refractive index, the same refractive index also, you can find the expression for refractive index also, because V2 is actually C by N1, and V1, sorry, V2 is C by N2, and V1 is C by N1. So you can substitute for this V2 and V1. You will get the expression for E0R in terms of refractive index. So we got the expression for the reflected intensity and incident intensity of electric field and magnetic field in terms of velocities or in terms of refractive indexes, N1 and N2. These are the expressions. 0T is 2N1 by N1 plus N2 times E0I. And as we know, intensity is half epsilon V E0 square. So the reflectance, we call it as reflectance. The reflected intensity R, it is the ratio of incident intensity, I mean the ratio of reflected intensity to the reflectance is the ratio of reflected intensity to incident intensity. So what is IR? IR is this IR, you can write half epsilon epsilon V1 E0 R square. And what is EI? It is half epsilon V1 E0 I square. Here we can use epsilon 1, and here also epsilon 1, because incident reflection in the same medium. Now when you take the ratio of these two, half cancel, epsilon 1 cancel, V1 cancel. So only E0R divided by E0I whole square will come there. We know E0R is N1 minus N2 by N1 plus N2 times E0I. So E0I times cancel. So that means this expression, if you need, I can write E0R can be replaced by E0I times N1 minus N2 divided by N1 plus N2. Here there's a square divided by, then there's E0I square already, E0I square. That cancel, and that is why this expression. Similarly, transmittance T is termed as the ratio of transmitted intensity to incident intensity. So transmitted intensity, what is transmitted intensity? IT is same way, half epsilon 2 will come there, V2 will come there, E0 T square will come. And incident intensity we already know. So here half only will cancel. Epsilon 2 V2 will come in the top, epsilon 1 E1 in the bottom, and E0 T by E0 I will come. Now let us see how this simplifies. Now let us calculate the transmittance. Transmittance T is incident, the transmitted intensity IT divided by incident intensity II. So transmitted intensity is half epsilon 2 V2 E0 T square divided by incident intensity is half epsilon 1 V1 E0 I square. Half gets cancelled. The other terms are there. Now we can substitute for E0 T. So T equal to epsilon 2 divided by epsilon 1, V2 divided by V1. E0 T can be replaced by 2N1 divided by N1 plus N2 E0 I, then there is a whole square, divided by E0 I already there, E0 I square. This E0 I gets cancelled. So this will give E0, E2 divided by E1, V2 divided by V1, then 4N1 divided, for N1 square divided by N1 plus N2 whole square. So now let us replace epsilon 1 and epsilon 2. How can we replace? Let us see. We know that velocity V equal to 1 by root of mu epsilon. So what is, we take the square on both sides, V square equal to 1 by mu epsilon. So epsilon equal to 1 by mu times V square. So here you can substitute, instead of E2, you can substitute mu 1 by mu 2 V2 square. So this become mu 1 V1 square divided by mu 2 V2 square. Now there is an into V2 by V1. Then there is a 4N1 square divided by N1 plus N2 square. Now again taking the approximation that mu1 and mu2 are very close to the value in free space, so you can cancel mu1 and mu2. Then V2 square and one of the V2 here cancel, and V1 and V1 is cancelled. Now what you're getting is V1 by V2 times 4N1 square divided by N1 plus N2 whole square. Now, what is V1? V1 is actually equal to C by N1. V2, it is C by N2. So you can write this as, instead of V1 by V2, you can write N2 divided by N1 for N1 square divided by N1 plus N2 whole square. Now one of the N1 cancel. That is why this expression 4N1 N2 divided by N1 plus N2 whole square. This expression for transmittance. And you can see that the sum of incident reflectance plus transmittance will be equal to 1. So R is the reflection coefficient or reflectance, and T is the transmission coefficient or transmittance. So R plus T is always equal to 1. So once you know the value of R or T, you can find the other value. Okay, so we discussed about electromagnetic wave at a boundary, or the reflection and the transmission of in an electromagnetic wave, the boundary of two linear homogeneous media, and the waves incident normal to the surface, or called normal incidence. So one part is reflected, another part is transmitted, and we calculated the expression for incident intensity, I mean reflected intensity and transmitted intensity in terms of the incident intensity. Also, we calculated reflectance and transmittance. Okay, I hope this is clear. Okay, students, thank you. Bye.